Good morning, everybody. Welcome back to another episode of Science with Mr. Emond. Today we're going to be continuing on in our unit of heat. We're going to look specifically today at a definition of thermal energy and heat, and also looking at specific heat capacity of objects, and then calculating how much heat is gained or lost from systems. Let's get started. So heat is defined as the amount of thermal energy. You're going to hear me interchanging these two words. Heat and thermal energy, they're going to be the same thing, okay? When we talk in common English, we usually use the word heat to describe how much thermal energy something has, but in science, we tend to use the word thermal energy, or words thermal energy. So heat is going to be the amount of thermal energy that's going to be flowing from one object to another. And the only reason heat would flow from one object to another is if there was a difference in their temperatures. And this is going to lead us to the first law of thermodynamics. The first law of thermodynamics states that energy will always flow from a hotter object to a colder object. So if you put a cup of coffee, and then if you take a cup of coffee and you put some ice cubes in there, where is the heat going to flow? Well, from the coffee to the ice cubes, from the hot object to the cold object. And as a result of the ice cubes gaining heat from the coffee, the ice cubes will start to melt. Okay? So that's just the first law of thermodynamics. It's quite an easy law, an easy one to remember. Heat flows from high heat to low heat, right? So anything that has more energy in it is going to lose its energy to the thing that has less energy. Hotter, colder. Looking at these two pictures, if we have an individual whose body temperature is 37 degrees, and he's sitting in a tub of water that's 42 degrees, where will the heat go? Well, the heat will go from the water to his body. Why? Because he is cooler than the water, so the water flows from warm to cold. And so his body temperature will start to increase. If we put the same individual in a tub whose water temperature is 20 degrees this time, where will the heat go? The heat will leave his body and go to the water. So he will essentially be heating up the water. And the temperature of the water will go up and his body temperature will go down. All right. This is going to get us into the big kind of words for this lesson, specific heat capacity. And specific heat capacity is going to be one of the units in the formulas we're about to see. It is a unit that basically is the quantity of heat energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So going back to this example, if I were looking at increasing the temperature of this water from 20 degrees to 21 degrees, and I were to ask myself, how much heat would be required to actually change the temperature of the water from 20 degrees to 21 degrees, and I were to measure how much heat that was, that would be the specific heat capacity of water, assuming that there was only 1 kilogram of water in this tub, which there appears to be more than that. But that's basically the temperature. If I have 1 kilogram of water, how much heat would it take to raise its temperature 1 degree Celsius? That's the specific heat capacity of water. And we can do that for pretty much any compound or element. We can ask ourselves, if we had 1 kilogram of that compound or element, how much energy would be required to heat it up by 1 degree Celsius? Once we find how much heat energy that is, how much thermal energy that is, we have found its specific heat capacity. And that number, that very specific number, can be used to calculate heat transfer. It can be used to calculate change in heat. It's a very useful number. So let's look at some examples. One thing to remember is that when we're talking about energy, the unit of energy is joules, right? This is a unit that I think many people are not familiar with yet, but you will get familiar with it. It is the standard international unit of energy, a joule. So for example, 903 joules of energy have to be added to raise the temperature of 1 kilogram of aluminum by 1 degree Celsius. So if I had on a hot plate 1 kg of aluminum, and this is, again, it's on a hot plate, right? So there's heat being added to the aluminum. How much energy would I have to put into the aluminum to raise it by 1 degree Celsius? Exactly 903 joules worth of it. So therefore, we can say that the specific heat capacity of aluminum is 903 joules of energy for every per kilogram and degree Celsius. So if I wanted to raise it by 2 degrees Celsius, 1 kilogram by 2 degrees Celsius, I just have to double this, right? This is your specific heat capacity of aluminum. 903 joules per kilogram Celsius. Water, this is a specific heat capacity that you're probably going to have memorized by the end of this class because you're just going to use it so often. Water has a specific heat capacity of 4.2 times 10 to the 3 joules per kilogram Celsius, which means that it takes 4.2 times 10 to the 3 joules of energy to raise 1 kilogram of water by 1 degree Celsius. One thing that I just want to make a connection. So in health science and in other health classes that you might have taken, we would have learned about what a calorie was. And a calorie is the amount of energy that is used when we're calculating the energy in food, right? 1 calorie is actually a specific heat capacity. 1 calorie is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. Okay? So it actually is similar. The difference is in calories, we're talking about grams of water, not kilograms of water. That's the difference. Here is a chart of different specific heat capacities of different substances. With this chart, you'll also be able to find it on Schoology. If you look at Schoology here, within our heat unit, in the first outcome, you will find the specific heat capacities here. And so you can always refer back to this. Again, remember, if there is something that we encounter in a problem that is not on this chart, make sure you let me know and I will add it to this chart. One thing to remember, not everything has the same heat capacity. I mean, that should be kind of obvious seeing as these numbers are very different, right? Everything has different heat capacities, and that's because some objects are easier to heat up than others. And we would know this, right? If you have ever been to a beach on a warm day, you know that the sand heats up very easily, right? It ends up being really hot and can hurt your feet to walk on, right? It absorbs a lot of heat, and the temperature of the sand can go up very quickly on a bright, sunny, warm day. The water doesn't do the same thing, right? The water heats up much slower. So if you can make it from your beach towel to the ocean or the lake, walking over that super hot sand, once you get to the water, it's not boiling hot, right? Which you might expect it to be. If the sand is super hot, the water you might think should be super hot too, but it won't be. And the reason why is because they have different specific heat capacities. Water has a really high specific heat capacity, meaning it takes a lot of energy to raise 1 kilogram of water by 1 degree Celsius, whereas sand has a very small specific heat capacity, meaning it doesn't take very much energy to raise 1 kilogram of sand by 1 degree Celsius. So they're going to heat up at very different rates, and that's why sand gets much hotter than water does on a bright, sunny day. So substances with low specific heat capacity, small values, warm up quickly because they don't need as much energy to change their temperature. But they also lose their energy very quickly, right? It can work in both directions. Having a low specific heat capacity means they can gain or lose their energy very, very quickly. Things with high specific heat capacities, they do the opposite. They take a long time to gain or lose their heat. This is also why coastal areas by the ocean, are milder in the winter and cooler in the summer. That's because water retains its heat, right? The water absorbs that heat, and it takes a long time for the water in the ocean to lose its heat, meaning it's going to be warming the air around that ocean water during the winter, which keeps those areas overall milder and a little warmer than where we are in the prairies, where there is no such thing happening. But the same thing happens in the summer. A lot of the heat gets absorbed by the water in the ocean, making the overall temperature cooler. So they might experience less of a temperature change than we would here. Okay, so now we're going to actually look at calculating the quantity of heat, which is going to be the unit Q. This is the quantity of heat or the quantity of thermal energy, right? Heat energy or thermal energy. And the amount of heat in a substance is going to depend on these three things. The temperature, right? And generally, the higher the temperature, the more heat energy is going to be present. That should be self-explanatory, right? The more temperature something is, like if you have something that's 100 degrees Celsius versus something that's 15 degrees Celsius, assuming it's the same substance, well, the one that's 100 degrees Celsius is going to have more heat energy. It's going to have more thermal energy. The next thing that matters is the mass. The larger something is, the more energy that thing is going to have. So here we're going to do a comparison of two things that are both 21 degrees Celsius, except one thing is much larger than the other. This one is 10 kgs and this one is 1 kg. Which object has more energy? This one. Why? Because it has more particles that have that same amount of heat energy. And when you add up all those particles together, it equals more heat than this one. Okay? And you can also think of it as how much energy would be required to heat up 10 kilograms of something to 21 degrees Celsius versus 1 kilogram of something to 21 degrees Celsius. This one would require way more energy, which means in the end, it has way more energy. And then finally, what substance are we talking about? And we know that when we're talking about this, we're really mentioning specific heat capacity, right? When we're trying to measure how much heat is in something, it's going to be a very different calculation if we're talking about how much heat's in water versus how much heat's in sand. Those are going to require very different specific heat capacities to calculate. All right. Now here's just a graph. Remember, if you're looking at something's temperature over time, and if you see something increasing very steeply, its temperature is increasing very quickly over time, and this is the same time, right? I'm drawing crooked, not the, let's get the line out. Let's say that this is the same amount of time, right? At this, whatever this is, maybe this is 10 seconds. Let's make it minutes. This is 10 minutes. After 10 minutes, if the temperature of this one, this substance, is much higher than this one and this one, if we were going to rank them, this yellow one would have the lowest specific heat capacity. And we know that because it increased by the most temperature. This one would have the highest because it was the most resistant to increasing its temperature. And this just comes back to the definition of specific heat capacity, right? It's the amount of energy required to increase 1 kilogram of that substance by 1 degree Celsius. So if this one is not increasing by very much temperature, it would mean that it has a very high specific heat capacity. If this one's increasing a lot, it would have a very low specific heat capacity because its temperature is just going up really quickly. This would be your example of water, and this would be your sand, right? And this one would be something in the middle of the two. Let's look at our formula. So here we go. Temperature is something that's easy to measure. All you have to do is use a thermometer. But heat has to be calculated using this formula. So if you ever see a question that says, how much heat? We're not asking for the temperature, okay? We're not asking for temperature. We're asking for you to input that temperature into this change in temperature over here and calculate heat. Q is the symbol for the quantity of heat or the quantity of thermal energy. Remember, those words are interchangeable. And we're usually talking about the amount of heat that something gained or something lost. And remember, that goes back to the first law of thermodynamics. Heat's always going to go from the hot object to the cold object. There's going to be a change in heat, so we want to know how much heat was gained and how much heat was lost. And I should say, there's going to be a change in heat, assuming that the two things aren't the same temperature. If you have one substance that's 21 degrees Celsius and another substance that's 21 degrees Celsius, and you bring them in contact with one another, will they exchange energy? No, they're the same temperature. And that actually is another law. It's the Zeroeth Law of Thermodynamics, and it states that if two objects are in thermal equilibrium, meaning they are the same temperature, if they're in thermal equilibrium, there will be no transfer of energy from one substance to another. In this equation, M is the mass, and the mass is in kilograms. So in the previous questions that we did, some students were having a little bit of difficulties because I would give you a unit of mass in grams and you would forget to convert it into kilograms or something along that nature. I would give you the temperature in Fahrenheit. So here's your delta T, your change in temperature. I would give you your temperature in Fahrenheit and you would forget to convert it to Celsius, right? So we have to be very careful. This formula, the units have to be the right units. So mass is in kilograms, temperature is in Celsius, and this new one here, C, lowercase c, that is the specific heat capacity. And its units are joules per kilogram Celsius. And where do you get this one? That's from the chart, right? If you know Q, M, and delta T, and you don't know C, you don't go looking for it on Google. You're calculating it, right? If this is the only unknown, then you find it yourself. However, if the question's saying, what's the mass, and it's telling you Q and delta T, well, that means they're assuming that you know C. So you need to refer to the chart, okay? All right, let's give this one a shot. How much heat is needed to raise the temperature of 2 kgs of copper from 20 degrees to 70 degrees? All right, so we're looking for how much heat. So Q is our unknown. That means we should know everything else. What's our mass? It's 2 kilograms. What's our specific heat capacity of copper? Let's go back. Copper is 3.9 times 10 to the 2. 3.9 times 10 to the 2 joules per kg Celsius. And we need delta T. Delta T is otherwise known as TF minus TI. We know our final temperature is 70. So 70.0 degrees Celsius, and our initial temperature was 20. 70 minus 20 is 50 degrees Celsius. Now this question becomes kind of easy. All you do is you plug it in, right? So our mass is 2.0 kgs. Our specific heat capacity is 3.9 times 10 to the 2 joules per kilogram Celsius. And our delta T is 50.0 degrees Celsius. All right, let's do some unit analysis here. We're going to have kilograms and kilograms cancel out, and Celsius cancel out, leaving us with just joules in the end. Now let's figure out what quantity of joules we'll have. So we need to do 2.0 multiplied by 3.9 times 10 to the 2 multiplied by 50. And that is going to be 390 times 10 to the 2. Let's be careful of our, well, first let's write that out. So 390 times 10 to the 2 is 39,000. Okay, let's be careful of our significant digits here. How many digits do we want? 2, 2, and 3. So we only want 2 significant digits, which our answer has that, and it should be in joules. So our final answer is 39,000 joules. Let's take a look at another example. This one's going to be a little bit different because we're finding what the final temperature is going to be. So we're looking for TF. Now, if we're looking for TF, that must mean we know what TI is, and it looks like the initial temperature is 10 degrees Celsius. So the initial temperature is 10 degrees Celsius. We also have the mass here. The mass is 1 kilogram, and it's an aluminum block. And so that means we are going to have the specific heat capacity. We just have to look it up. An aluminum block, where's aluminum? There it is, 9 times 10 to the 2. So our aluminum block is 9 times 10 to the 2 joules per kilogram Celsius. I just want to double check my sig figs. Yeah, they gave me 2. Okay, and do we know anything else? We need to know delta T. No, we don't know delta T. We need to know Q. What is Q? Here it is. 3.0 times 10 to the 4 joules of heat is being added. Okay, we have everything we need here, but we're going to need to do a little bit of rearranging of our formula. So we currently have Q equals MC delta T, but delta T, remember, is TF minus TI. And what are we trying to isolate here? TF. So we're going to need to get everything away from this TF. Let's start by isolating our parentheses here. So we're going to get rid of MC. So we're going to divide both sides by MC. What this is going to do is eliminate these, leaving us with just our parentheses. So now we're one step closer. We have Q over MC equals TF minus TI. And what are we trying to do? Isolate TF. So let's get rid of TI by adding it to both sides. Adding it to both sides is going to eliminate it from this side, leaving us with our final equation, Q over MC plus TI equals TF. Okay, now that we have this lovely formula here, we can plug everything into it. So I'm just going to do something called, I'm going to swap the two sides, right? And the only reason I'm doing this is I want my TF to be on the left side because that's the way we usually write, right? Is something equals something else. So TF equals Q. So 3.0 times 10 to the 4 joules divided by my mass. My mass is 1.0 kilograms multiplied by our specific heat capacity, which is 9.0 times 10 to the 2 joules per kilogram Celsius. Okay, now we're going to do some unit analysis here. These kilograms are going to cancel out. These joules are going to cancel out. And all we're going to be left with is Celsius in our denominator of our denominator, which means it's going to become our new numerator. And that is some math skills, right? Okay, now we're going to plug this into our calculator. So we're going to switch to our TI Inspire here, and we're going to start plugging things in. So 3 times 10 to the 4 is 30,000. We're going to divide that by 1 kilogram, which is still 30,000. Then we're going to divide that by 9 times 10 to the 2. And we get 33.33. So TF is equal to 33.33. Now remember that this is actually supposed to be Q over MC plus TI. So we need to add TI to this, and TI is 10 degrees Celsius. We also want to be careful about our significant figures, right? We have 2 sig figs in all of these. So we should only have 2 sig figs in our expression here. So this should just be 33 degrees Celsius. Now, 33 plus 10, our final temperature is 43 degrees Celsius. When you add digits, you use the number of decimal places. So that was 10.0, right? In the question? Yep. So this is going to be 43.0 degrees Celsius. And there you go. So now we're going to do 2 where you guys are going to do the work. This first one is an easy one, like the first one I did. The second one's a little bit harder. Give it a shot. So for those of you on YouTube, go ahead and pause the video now and come back when you're done. See you soon. For those of you on YouTube, welcome back. Let's go through the solution. So we knew that there was 3 kilograms of water, and its specific heat capacity is 4.18 times 10 to the 3 joules per kilogram Celsius. We know that our final, it's going from 80 degrees Celsius to 10 degrees Celsius. So this is our initial temperature, and this is our final temperature. So when we do TF minus TI to find delta T, it's 10 minus 80, which is negative 70 degrees Celsius. Now you just plug these numbers in to your formula, and you solve it, and you will get a negative 878,000. But again, we're going to be rounding to 2 significant figures, so that would be negative 880,000 joules. All right, so let's give this one a shot. We know that 2.52 times 10 to the 4 joules of heat are being added to 2 kilograms of mercury to reach a final temperature of 130 degrees Celsius. What is the initial temperature of mercury? So you're going to want to split your formula up from this general form and change delta T to TF minus TI. Give this a shot. Start by finding your givens and then just plug them in and rearrange. You may want to rearrange your formula before you put numbers in. Just do what's more comfortable for you. When you're done, come back and we'll have the solution waiting for you. Pause now. Welcome back. We have the solution worked out for you here. So we know that we have a heat gain of 2.52 times 10 to the 4 joules. And you have 2 kgs, so that's your mass. We know that it's mercury, and if you look up the specific heat capacity of mercury, it's 1.4 times 10 to the 2. And the final temperature was 130. This is the information we're given, And what we're looking for is Ti. So now you can rearrange your formula to isolate Ti. So the first step is to divide by MC to get rid of these. You'll be left with Q over MC equals TF minus Ti. And there's a few things that you can do from here. I prefer adding and subtracting. I think that's easier. So you're going to get rid of negative Ti by adding Ti, which is going to make it Q over MC plus Ti. And remember, we want this to be by itself and we want it to be positive. So that's why I moved it to the other side to make it positive. Now I'm going to get rid of this whole thing by subtracting it to the other side. And you're left with Ti equals TF minus Q over MC. And this is the formula that we're going to use. So we're going to substitute all our givens into this formula. So TF is 130. Q is 2.52 times 10 to the 4. Our mass is 2 kgs, and here's our specific heat capacity. So we plugged everything into our new formula, and then we put this into our calculator and found it to be equal to negative 90. Or just plain 90. The negative sign was there before, right? So 90. Now we have 130 minus 90, and that's 40. So our initial temperature in this problem was 40 degrees Celsius. That's it for today. See you next time. Bye-bye. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.